Have you ever stopped to think like how we actually describe complex movements or forces in the real world? I mean, things like the twist of a wrench when you're tightening a bolt or, the spin of a whole planet out in space. Sure, basic math helps us count things up, add numbers together, absolutely. But when you need to understand not just how much force, but which way it's going, direction, magnitude, how things are oriented in 3D space, well, simple adding and multiplying just doesn't cut it. So today we're taking a deep dive into a tool designed for exactly that, the cross product. It's fundamental in vector calculus, a really powerful concept for getting a handle on these directional forces and spatial relationships. We'll look at what it is, how it's defined, some surprising geometry behind it, and importantly, where it actually shows up in physics. We're drawing our insights from some great source material today.
Yeah, our mission here is basically to unpack these sometimes dense mathematical ideas and make them clear, maybe even relatable. Think of it as a shortcut to understanding this powerful tool without getting, bogged down in textbook jargon.
Okay, so let's unpack this. The cross product. At its most basic level, what are we talking about? It's an operation, right? It takes two vectors quantities with both size and direction, and it produces a third vector. And that's a really key difference straight away, isn't it? Compared to, say, the dot product, which just spits out a single number, a scalar.
That's exactly right. And it's important to stress this isn't for just any old vectors. It's specifically defined for vectors in three-dimensional space, as mathematicians call it. Another crucial piece mentioned in our source is the need for a right-hand coordinate system. This isn't just some arbitrary rule. It basically sets a standard. If you line up your right index finger with the positive x-axis, your middle finger with positive y, your thumb has to point along positive z. It ensures consistency. Everyone using the cross product gets the same directional result. Otherwise, well, it'd be chaos, wouldn't it? Different answers depending on how you set up your axis.
Right, it locks in the orientation. And speaking of direction, the right-hand rule itself is such a neat kind of physical way to get it. If you're listening, you can try this. Imagine pointing your right index finger along the first vector, let's call it us. Then point your middle finger along the second vector, v. Keep your hand fairly natural. And your thumb. It just points in the direction of the result, the cross product u x v. You can even visualize this with the basic vectors I, j, and k that define the axes.
It's a very handy visual, yeah. And using that rule, we can see how it works for those fundamental unit vectors. So index finger along I, x-axis, middle finger along j, y-axis, and points up along k, z-axis, so ix, jx, k. And similarly, jxk, I, and kxi equals j, following the cyclic pattern. But here's where it gets really interesting. It shows a critical property right away. What if you swap the order? Index finger along j, middle finger along I, now your thumb points down towards k. So jxi equals k. And the same logic gives us kxj equals I, and ixk equals j.
Ah, so the order completely flips the direction of the result. That's huge. So uxv is definitely not the same thing as vxu.
Absolutely not. They're opposites. uxv equals vxu xu.
Ah.
This property is called anti-commutativity. And think about why that's so useful, going back to the wrench example. If rxf gives you the tightening direction, maybe clockwise, then fxr would have to give you the loosening direction, counterclockwise. If they were the same, if it was commutative, the math couldn't tell the difference between tightening and loosening. So this non-commutativity isn't just some weird math quirk. It's essential for describing directional things like rotation.
Okay, that makes perfect sense. It encodes the which way aspect, so we know what it is, roughly, and its core directional property. But how do we actually calculate it for general vectors, and are there other behaviors we should know about?
Right. Well, we don't need to grind through the full calculation here, but yes, there's a definite formula. If you have ui plus ui plus ui plus ui plus ui plus ua show, you can calculate the components of uxz directly. The formula looks a bit like ui for the component, and similar patterns for j and k. Often people use a mnemonic, like a 3x3 determinant, to remember it. The main point is, it's a well-defined calculation. You plug in the numbers, you get the resulting vector components.
Got it. Good to know there's a systematic way, even if we skip the nitty-gritty. So what about other properties? Does it play nicely with addition or scaling?
It does, actually. The source lists a few key ones. First, it's distributive over addition. That means uxv plus w is the same as uxv plus uxw.
Oh, okay. So if you have multiple forces acting, say V and W, and you want the combined torque from U, you could calculate the torque for each force separately and just add the results.
Exactly. You can break the problem down. Makes things much simpler sometimes.
That sounds very useful in practice.
And it also handles scalar multiplication predictably. If C is just a number, then CUXV is the same as UXV, which is also the same as UXCV. You can basically pull scalar factors in or out wherever it's convenient.
So again, thinking about torque. If I double the length of my wrench arm, I just double the resulting torque vector. Simple as that.
Simple as that. The scaling factor just carries through. Very intuitive. Now here's another property, one with a really clear geometric meaning. If two vectors, u and v, are parallel, then their cross product, uxv, is the zero vector, a vector with zero magnitude.
Ah, that's a great diagnostic tool then, isn't it? If you compute a cross product and get zero, you instantly know those original vectors must be pointing in the same or exactly opposite direction.
Precisely. It's a very clean test for parallelism.
Okay. And we talked about it not being commutative. What about associativity? Like with regular multiplication where ABC is the same as ABC. Does that work here?
Good question. And the answer is a firm no. The cross product is not associative. So uxvxw is generally not the same vector as uxvxw.
Wow. Okay. So the order you perform multiple cross products in drastically changes the final result.
Immensely. You absolutely have to pay attention to the parentheses or the order of operations. It's not like adding numbers where the grouping doesn't matter. Here, it fundamentally changes the outcome vector.
Right. Like building something, the sequence matters. Attaching A to B then C is different from B to C then A. The final shape is different.
Okay, that's a really important distinction. So we've got the mechanics, the properties.
Yeah.
But you mentioned geometry. This is where it starts to get really visual, I imagine.
Absolutely. This is where the cross product really comes into its own, revealing some beautiful geometric truths. One of the most fundamental is orthogonality. The vector you get from the cross product, uxv, is always perpendicular to both of the original vectors, u and v. Always.
Always. So like if u and v are lying flat on a plane,
their cross product uxv will point straight out of that plane at a perfect 90-degree angle to both of them. Think of it as the normal vector to the plane defined by u and v, like a flagpole sticking straight up from the ground, defined by the two vectors. That's a really powerful concept. It defines the orientation of that plane.
Exactly. And it gets better. If we look at the magnitude, the length of this resulting vector uxv, it also tells us something geometric. The formula for the magnitude is uxv equals uv sin, where E is the angle between U and V.
Okay, UV sin. That sounds familiar from geometry. What does that represent visually?
That value is precisely the area of the parallelogram that's formed when you place the vectors U and V tail to tail.
Ah, of course. Base times height, effectively. The length of V times the perpendicular component of U, which is U sin. So the length of the cross product vector is the area of the parallelogram they span.
You got it. It's a direct geometric readout. And think back, if U and V are parallel, θ is 0 or 180 degrees. Sine of that is 0. So the magnitude uxv is 0, meaning the area is 0, which makes perfect sense. And it confirms our earlier property.
Yeah.
uxv equals 0 for parallel vectors. It all ties together.
That's really elegant. Area from a vector operation.
And we can even take it one step further into 3 dimensions, using something called the scalar triple product. This involves both a cross product and a dot product. You calculate uxv OW. So you take the cross product of u and v, which gives you that perpendicular vector, and then you take the dot product of that vector with a third vector, w.
Okay, so cross two vectors, get a new vector, then dot that with a third one. What does that number tell us?
That number, its absolute value, gives you the volume of the parallel piped, formed by the 3 vectors u, v, and w when placed tail to tail.
A parallel pipe, like a squash box, right? Defined by those 3 vectors as adjacent edges.
That's the shape. So this combination of operations gives you the volume of that 3D shape. It's a remarkably compact way to find the volume using just vector algebra.
Wow. Area from the cross product magnitude, volume from the scalar triple product. That's pretty amazing. Okay, so we've covered the math definitions, the properties, these cool geometric interpretations, but let's bring it back down to earth. How does this actually, apply? Where do we see it in action?
Great question. And a perfect, really tangible example is torque. Torque is just the rotational equivalent of force. It's what makes things twist or spin. And in physics, torque, usually symbolized by tau, is defined as a cross product. Specifically, it's HEAR-XF, where R is the position vector from the pivot point, like the center of a bolt, out to where the force F is applied, say, on the handle of a wrench.
The wrench example again, we've all felt this, right? Trying to loosen a really tight nut.
Absolutely. And the math matches the experience perfectly. The magnitude of the torque is HERF sin. Think about it. To get the most turning force, the maximum torque, you push perpendicular to the wrench handle, right? That's when 90 is 90 degrees and C 90 degrees is 1, maximum value. But if you try to push straight along the wrench handle, towards or away from the bolt, that's CC or 180 degrees, sin to 0. You get no torque, no turning effect, no matter how hard you push in that direction.
It just doesn't work. Yeah, that makes total sense. And it reminds me of that old Archimedes quote, something like, "Give me a lever long enough, and I can move the world." He understood that increasing R, the lever arm length, dramatically boosts the torque, the turning force. It's amazing how that ancient idea connects directly to this cross-product calculation.
It's a fantastic connection, yeah. Shows these principles are timeless. And the cross product is so elegant because it doesn't just give you the amount of turning force, the magnitude. It also gives you the direction of the twist. Is it tightening, clockwise maybe, or loosening, counterclockwise? The direction of the vector tells you the axis and sense of rotation. Trying to describe that directionality without the cross product would be, frankly, a real pain. You'll need separate rules or conventions. This packs it all into one operation.
So it neatly captures both the how much and the which way of the twist. Brilliant. Okay, before we wrap up, it feels important to quickly compare the two big vector products we've touched on, the dot product and this cross product. They both involve two vectors, but they're fundamentally different tools.
Yeah, definitely worth clarifying the distinctions. Let's recap the main points. First, the result. Dot product, UEV, gives you a scalar, just a number. Cross product, UXV, give you a vector. Completely different types of answers.
Right, number versus vector, big difference.
Second, the geometric meaning of their magnitudes. Dot product, through UVAs, tells you about projection, how much one vector lies along the direction of the other. Cross product, with UVSN, tells you about the area of the parallelogram they form, relating to their perpendicularity.
So kind of like alignment versus area span.
That's a good way to put it. Third, when do they result in zero? The dot product is zero if the vectors are orthogonal, perpendicular. The cross product is zero if the vectors are parallel, opposite conditions.
Okay, orthogonal for dot zero, parallel for cross zero. Got it.
And finally, commutativity. The dot product is commutative. UVAV is the same as VU, EUF, order doesn't matter. But the cross product is anti-commutative. UXVU, EVXU. Order reverses the direction.
These differences really highlight how they're suited for completely different jobs, don't they? Calculating work done might use a dot product, while figuring out angular momentum needs a cross product, both essential but for different aspects of physics and geometry.
Exactly. They're complementary tools in the vector calculus toolbox. And thinking about all this, how the cross product defines rotation, surface orientation, twisting forces, it kind of leads to a final thought maybe for you, our listener. Now that you have maybe a deeper feel for this operation, how might it change the way you see the world around you? When you look at, say, a spinning gyroscope, or the structure of a bridge, or even just opening a door, can you perhaps appreciate a bit more the unseen geometry, the directional forces at play, all governed by principles that the cross product helps us describe? It's sort of a hidden language, isn't it? Something to think about.